In this lecture, we shall learn how to convert decimal to binary number and vice versa. To know this, we need to first understand how a decimal number is represented as a binary number. The idea here is to convert any given decimal number into sequences of zeros and ones. So the question really boils down to how do I convert any given number into the sequences of zeros and ones. To achieve this, we may use the Euclid's division algorithm that you may have probably learned in your high school. Don't worry about the name of the algorithm. It's quite simple. Any integer number a divided by the divisor b shall yield the quotient q and the remainder r. Euclid's division algorithm says that the remainder r is always greater than equals to 0 and less than b. For example, if you divide any number by 5, the remainder can be either 0, 1, 2, 3 or 4. Remainder cannot be anything else apart from 0, 1, 2, 3 and 4. Try dividing 14 by 5. Remainder is 4. Try dividing 31 by 5. Remainder is 1. Try with 20. Remainder is 0. Try dividing any other number with 5. The remainder you get shall always be 0, 1, 2, 3 or 4. It cannot be anything else. So can we take an advantage of this Euclid's division algorithm to convert any number to 0 and 1? Your guess is correct. If we divide any decimal number by 2, remainder would be either 0 or 1 and nothing else. Wow! Let us try doing this calculation by converting decimal number 6 into binary. First divide 6 by 2. 2 times 3 is 6, the remainder is 0. Now divide 3 by 2. 2 times 1 is 2 and the remainder is 1. Now you need to divide this 1 by 2. 2 times 0 is 0 and the remainder is 1. We stop right here as the quotient now has become 0. Now you have to note down all the remainders in the sequence from the latest one to the oldest one. So you get 110 as the binary number. That's all. We are done. Binary number of decimal 6 is 110. Using this technique, you may represent any given number into its binary form. Let us take one more example of converting decimal 9 into binary. First, let us start by dividing 9 by 2. 2 times 4 is 8, remainder is 1. 2 times 2 is 4 and the remainder is 0. 2 times 1 is 2 and the remainder again is 0. 2 times 0 is 0 and the remainder is 1. We stop our calculation here as the quotient has become 0 now. Catch hold of remainders from bottom to top. We get 1001 as a binary equivalent for decimal number 9.
Hey Sunil, this is all good, but how do I convert binary to decimal? How do I convert 1110 into decimal?
Good question, my friend. To answer your question, let me make some inquiry. I hope you won't mind, right? Let us consider a decimal number 297. It has got 3 digits, digit 2, digit 9 and digit 7. Out of these 3 digits, which one do you think is the most powerful one? If you think that digit 9 is the most powerful digit in the number 297, then we need to fix some of your concepts. The location or position of a digit determines its real value. In this number 297, that is 297, digit 7 is at units place, digit 9 is at tens place and digit 2 is at hundreds place. We can in fact write 297 as 200, 9 tens and 7. That is 2 times 100 plus 9 times 10 plus 7, which is equals to 2 times 10 to the power 2 plus 9 times 10 to the power 1 plus 7 times 10 to the power 0. Adding all this together, we'll get 297 as the answer. In this case, the power of 10 is used as the decimal number system is of base 10. We may use the same concept to find the decimal equivalent of 1110. Here, we shall use power of 2. as the binary number system is of base 2. We have 0 at 2 to the power 0 equals to 1's place, 1 at 2 to the power 1 that is 2's place, next 1 at 2 to the power 2 that is 4's place, and the last one at 2 to the power 3 that is 8's place. Multiply 0 with its place value 1 plus multiply 1 with the place value 2 plus multiply 1 with place value 4 plus multiply 1 with place value 8. The answer is 0 plus 2 plus 4 plus 8, which is equivalent to 14, 1414. So we say that the binary 1110 is equivalent to decimal 14. That's all. I hope I answered your question. In the binary number 1110, the first one is the most significant bit, MSB, because its place value is 8, which is the greatest place value, and the last bit 0 is the least significant bit as its place value is 1, which is the least place value. That's all in this lecture. We have learned how to convert binary to decimal and vice versa. See you in the next lecture. Stay tuned.